Wow. Okay, so we're going to start this session. I guess it's the last one today. So I'm Moustapha. I work for Facebook AI Research. So I will do a quick session on, it will be mainly practical after Andrea's session. I guess you grasped most of the material on neural networks, just basically understanding that it's a composition of function and nothing fancier. You can do very complicated stuff, but at the end of the day, it's just a composition of function, and applying the chain rule, you can train models that can do many different things. So what I will do first is to show you a couple of applications where we use concrete neural network models in production and for demos at Facebook. And then we will have a practical session with PyTorch, which is a framework that we use internally and which is open source now to design complicated neural network models that you will be able to do it at the end of this session. And for most of the applications that I will be showing, at the end of this session, I will point out to code that you can just take and customize and reuse it to do whatever you like with it. So there are a lot of things that neural networks are used for at Facebook, mainly for perception tasks, understanding and learning, for predictive modeling, and also for planning, right? So when I say perception, the first thing that comes to mind is visual recognition, which is classification, image segmentation, and pose estimation. So 5 years back, what we could do is given an image to recognize the different objects that are in the image, including persons, etc. So we have made some progress. In 2015, we could, even before we could do that, but we could do it even better with neural networks doing some image segmentation with more objects in addition to just doing the classification. And more recently, some of our colleagues at Facebook AI Research developed this mask, RCNN, that allows you to do very accurate semantic segmentation and recognize even more objects. And now, the state-of-the-art models allow you to do both object recognition, semantic segmentation, which is you detect the exact contours of the object of interest in the image, and also to infer the skeleton of the people that are in these images. So these things are used for many different applications, obviously for object recognition and image classification, but we also use it for example, tracking and action recognition and this type of applications, right? So if you can track people and predict their actions, etc., in the internet. Right? So you can also use it to, to localize people and also do action recognition for various types of applications, right? And now we can train models that are small enough to perform these tasks and then run them on device. So these are real applications. So another thing you can do, which Ralph was mentioning, you can, this already existed. You can have it in Adobe, but now with neural network, you can have these applications more accurate than other approaches that do exist. Neural networks are not the only way of doing this. They're certainly some of the most complicated and less efficient way of doing it. But if you really want something that is very accurate and state-of-the-art, you will probably have to resort to them. But there are simple ways to tackle these problems, obviously, right? So it is also used to do augmented reality and all these things, fancy stuff, right? So in understanding and learning, because intelligence is not just about perception, you can use the models that you develop for image recognition, for example, or object recognition or whatever, to do scene understanding or image interpretation, right? So they call it now captioning. This is a very popular task in the community, and it allows you to do these kind of things. So given an image, not just say what are the categories that are inside, but train a model that directly describes what's going on in the image, right? So this thing is actually used in production, and it allows people who have limited accessibility problems, for example, who are blind, to be able to use Facebook, for example. So another thing is to learn to interpret textual representation and answer questions about those textual representation. So there are a set of tasks called baby tasks. So they were introduced in 2015. And it turns out that you can train models that read some corpus and answer questions about those corpus. This is a very difficult task because when these simple problems that you see here, when they were introduced in 2015, the existing neural networks could not solve any of these problems. But you could find other methods that could solve some of them, but not the neural networks. So people in the community have introduced various models called, for example, the end-to-end memory network, which allows you to solve very simple problems like this one. So John is in the playground, John picked the football, Bob went to the kitchen, and then when you say, where is the football, the network can answer that it's in the playground. So this is very simple, and then recently people have started to answer more complicated questions with entailment structure and these kind of things. Right. So these are very simple tasks. Actually, they're just built as unit tests to test the models and see what they can do and what they cannot do. But ultimately, what people would like to do is to go beyond these things and then answer any type of questions that whose answer exists in a knowledge base. Let's say Wikipedia, for example. So one of the things that we are doing at Facebook is to develop methods that allow reasoning and chatbots. I think Ralph has talked about language and conversational stuff this morning. So this is a typical example of that. So you can take a neural network model, a sequence-to-sequence model, and train it on Wikipedia, and then use it to design a chatbot that allows you to answer all sorts of questions if the answers are in Wikipedia. So for example, you have this where you can say, who invented convolutional neural networks? So the chatbot will interpret this question and then try to find the answer on Wikipedia, and then put the answer in shape and say, I would say Yann LeCun, but I might be wrong, so it's not very certain. So you make it act a bit like a human. So these are some sort of cool things that you can do with the existing models. So one thing people are very excited about is also quote-unquote predictive modeling. So learn the physical laws of real life. So having, for example, seen a certain number of images, you can learn to predict what's going to happen next, right? So if you want to predict the future in videos, for example. So this is a very difficult task, and these kind of things, typically show you the limitations of the existing models. So there are progress on this topic, but it really shows you what the models can do now and what they cannot do, right? So people also use it to learn to do intuitive physics. For example, if you put objects on top of each other this way, what will happen, etc. It's very interesting stuff. Yeah. So you can also use the models, and all of these things are just some variants of the building blocks that Andreas talked about in the previous talk, right? It's always about convolutional networks, complicated architectures, yes, but just convolutional networks at the end of the day, or recurrent neural networks if it is sequential models. So people design all these things to solve these kind of tasks. And one of the things people are interested now is the task of planning. So planning is a very important task, because if you have heard of self-driving cars, for example, you have to have strong planning components to be able to solve this type of problems. So there are people working at FAIR on these problems, mainly more controlled experiments like in RTS video games, like StarCraft, for example. So here you can see, you can train a network, a reinforcement learning-based network, to do micromanagement of different units and then play the game of StarCraft. So this is interesting because it allows you to, all the algorithms that you can develop in this scenario can be, in some sense, scaled to more complicated problems like self-driving cars, etc. So with neural network, you can do a lot of stuff with deep learning models. They are not the alpha and the omega. Of course, you can solve problems with other methods. And in fact, if you face a problem, you should always try to do a simplest approach possible to see if you can solve it first before jumping to a gigantic neural network. But if it doesn't work, then yes, it's very recommended to use these approaches because there are a lot of open source code available, and people are gaining more and more knowledge about how to train them efficiently, etc. Right. So in general, you have here in green all the tasks that people can solve very well now with deep learning models, right? In yellow, you have the tasks that, you know, people can somewhat solve or demonstrate working models on it, and everything is red. In red is tasks that we don't have solution on it. Like you can think about all these things like long-term planning, human quality, automatic translation, etc. For very narrow domains, yes, but for open-ended stuff, this is definitely not the current models definitely cannot solve these problems. So there is no magic here. Deep learning is very powerful, but it cannot solve all your problems. And the main reason is, and I think Andreas have talked about it, is all the algorithms that you have now, they're very data hungry, right? They're not data efficient. So they require a lot of data, mainly a lot of annotated data, which means like you will spend a lot of money to build a supervision to train your models. So the real challenges now in this topic is really how to learn with few data and with as less supervision as possible. Right? Okay. So what we will do now is I will show you the IPython notebook. So what we will be working on is mainly this thing. This thing called PyTorch. So PyTorch, if you can open the notebooks, you will see it. It's, do you have access to the notebooks? No? So I will just give a 15 minutes blitz. Yeah, you can, yeah. Yeah, please.
Torch is on the...
Yes, but not PyTorch. This is Lua Torch.
Yeah, I'm looking.
PyTorch is not in there.
It's not in there, right?
No, it's not. It's not in there. We have to install it. It's weird, right? But it has been released like 2 months ago or something like that. So.
Let me ask a question to the team that does it.
Yeah, you should. Just Torch is in there. PyTorch is way better.
Not in the image, not PyTorch.
Can I show you?
Yeah, of course, yeah. Please do, yeah.
Oh, right, cool. Can you connect to the... Sorry. Should be on here.
DSA1, you do?
Ah, this is on. Oops,
No, that's not the one.
Yeah, it is. That's the one I want. I want DSA...
No, you want one. Yeah. Yep.
It's actually too sensitive. Yeah, that's the one. This is the one I want.
Okay.
Yeah. So DSA 2017 is what you want, okay? So anyone who can't connect, it's because you've not, if you can't find the web page, it's because you've gone to the wrong hotspot, okay? And then you go to 192.168.1.114. Come on, yeah, good. Then you scroll to the bottom, and then you click here. And so this is where you run the notebook and stuff on a remote server, which is one of the handy things about Jupyter, is it lets you do this. So this morning, when Ralph was demonstrating, did you use the notebook? You didn't even, did you? Okay, but the cool thing is...
I ran it on my machine.
Yeah, okay, my bad. Okay, but anyway, the idea is that you, when you set up your AWS instance, you could run a notebook there, and then you could... Yeah, you did. Okay, cool. Just checking. Yeah, you did exactly what he did. So you're doing exactly what he does. So you can click here. Be somewhat patient. I think everyone's just doing this simultaneously now, which could be a problem. And then you can, if you follow the link, you can make an account. You can make a notebook on here. So you enter here your like a unique username. So
Moustapha.
Moustapha, you should spell your name. You might already have it actually. You
Yeah.
can make it a new one. I think we've already made you. So if you've already been made, I think we'll find it will say like that's not unique. Probably. Oh my god, the server's now being hammered slightly. Oh well, anyway, that's the idea. It might take a few seconds until everyone's made an account. That's probably.
Yeah, you make an account and then you just the step 2 is just you click on a Jupyter Notebook server.
Yeah.
Should work, right?
Maybe I'm optimistic what a laptop can provide. Cool. Well, anyway, it might take a few seconds until everyone's got it set up. So you can
Yeah,
and then you'll be somewhere
works.
in here. Oh, come on, it's not loaded. Reload. Come on. Ah, where are they all? What?
Actually, the reason I think is because I did not submit a query.
I know it should still like list them all.
Yeah.
Anyway, it might take a few seconds for it to like work. So I'm just going to see what my laptop's up to, see if it's getting a bit
Okay.
hot. But anyway, that's how you do it. So it might take you all a few seconds to get to it.
So have you managed to get to this point?
Oh, cool. Okay. I've noticed like there's 100. I guess most people have got it.
So who has managed to open this? Do you see a listing of the different files there? Do you see a list of different files here? Okay, cool. So probably there is problems with my stuff. So who sees a list of files here? DSA, oh, it's not available? Oh. Seem to be working. Yes. Oh, what? Yeah, that's what I'm going to do. You're right. Okay, so while you were getting set up, I will just go through the basics of what PyTorch can do for you. So if you remember Andrea's talk, he did show you how to implement a simple neural network with Numpy and do stochastic gradient descent to train the weights of the network and get it solve your prediction task. It turns out that you can do that more easily with a framework that allows you to do automatic differentiation and that allows you to build complex models in a very easy way by composing building blocks, right? So PyTorch is one such library. There are others like MXNet, which he talked about, and other ones which are not good. So So yeah, so
They won't disagree.
okay, so cool things about PyTorch is that you do not have to compute or to write down the gradients, the chain rule yourself, because when you design the model, because it has an automatic differentiation engine, it automatically computes the graph and then infers the gradients for you. So what you need to do is just to declare your model, your loss function, and then everything else follows from there because of the Autograd. Okay. So another key feature of it is if you know Numpy, this is very easy to use because it has a seamless integration with Numpy. In fact, basically the nomenclature, if I can call it that way, is basically the same. So you can just consider it as a layer on top of Numpy that allows you to do more complicated stuff, use your GPU to accelerate your matrix multiplication, etc. So also there are a lot of optimization algorithms that are implemented inside. So Andreas showed you how to do stochastic gradient descent. There are more complicated algorithms, which are all of them variants of stochastic gradient descent. You can read the papers or the textbook notes about those algorithms, but you actually don't need to re-implement them. Once you understand the basics, you can just go in PyTorch and select the optimization algorithm that you want, and then it will do the rest of the job for you. Okay. So it also has a lot of data loading utilities. In fact, most of the models that I presented in the first part of my talk, I will point you to actual code in PyTorch that you can go and download and use and start editing and customizing to your own needs. Okay. So it has basically the same structure as the NumPy basic data structure, which is the ND array. So you have in PyTorch you have the Torch.Tensor, and then all the other operations that you can do on the ND arrays in NumPy, you can do them on these tensors, right? And you can accelerate them on your GPUs. So these are two examples of codes. Like on the right, on your left, you have the NumPy version of the code, and on your right, you have the PyTorch version of the code. And if you look at it very precisely, it's basically the same code. It's exactly the same thing, very few changes. Right? So it's very easy to use. Have you guys managed to get access to the notebook? Okay. So here are a few examples. Yeah. I can do it live here, but then yeah, I can give examples live here, and then whenever you are able to access the IPython notebook, then you can just try and train. Yeah. Okay, so I will go over the slides. It's okay. Let me just go over the slides, and then after I will answer questions individually. If you want me to help you troubleshooting or these kind of things, we can even set up a Facebook group where you can ask questions. I will answer all sort of questions. That works as well. Right? Facebook groups are very useful, actually. Use them more. They're very useful. Yeah. So yeah, once you install this PyTorch, it's available on Anaconda. So if you are on Unix, you can just do conda install PyTorch, and it will install the right version for you. And then it's very simple to use. Just import the library and use declare tensors as you would use ND arrays in NumPy, and everything else is basically the same as in NumPy. Okay, you can do matrix multiplication. You can generate random matrices by using torch.randn instead of numpy.random.randn. Okay, print sizes x.size instead of x.shape. So it's very, very similar to what you know in NumPy. So the indexing works exactly the same way, okay, as in NumPy. right? So it has a seamless integration with Numpy, which means that if you have a Numpy ND array, you can convert it into a Torch tensor. And yes? Yes? Okay. So if you have a Numpy ND array, you can convert it to a Torch tensor, and there is no copying while you do that. So it's very efficient, just like a link between them. So there is no copy. So it's no additional memory overhead. Right? Okay. So you can do basic operations like adding matrices, subtracting, multiplying, you know, all your favorite linear algebra stuff. It's very easy to do. So whatever, what I would suggest is just to take the example that Andres gave you and then re-implement it in PyTorch. That's the first thing that you can do. Whenever you can access this, the notebooks, I have given several different examples which are gradually complicated that allow you to design more and more complicated models. Okay. So yeah, you can convert NumPy tensors to NumPy ND arrays to Torch tensors and back and forth. You can just, whenever you have a tensor in Torch, you can put it on GPU and perform all your operation in GPU by just coding .CUDA, and then it puts it on the GPU. Everything else you compute it as you would do it without the GPU. You know, seamless integration. There is no fancy operation to do, no manual GPU programming, no nothing. Okay. And most important, you can do automatic differentiation. So this is very useful. Andres have shown you the Inception V3 model, which is a very complicated architecture that Google uses now to do visual recognition mainly. It's very difficult to train those kind of models if you don't have an automatic differentiation, because every time you come up with a new architecture, you have to manually, if you don't use automatic differentiation, you have to manually write down all the gradients at all the different nodes of your model. So that makes the research process very slow. So if you have a tool that allows you to do automatic differentiation, you can experiment with different architectures and different models more quickly. Okay. So the way it does it is as this. So you just declare variables. So Torch has something that you call you call the variable class of Torch.Autograd. For every tensor, you declare it as a variable. So it's this line, x is declared as a variable. The hidden layer h is declared as a variable. The weight matrices wx and wh are declared as variable as well, right? So you define your computation graph by declaring these operations. So you say that the hidden layer, the first hidden layer, the I to H, which is the input to the hidden layer, it's just a torch.mm, which is a matrix multiplication of wx and x, right? So when you want to go, as in the Andres example, if you want to go to the input to the first hidden layer, you just multiply your input with a w, with your w matrix, okay? And if you want to go to the hidden layer to another hidden layer, you multiply the output of the first hidden layer by another weight matrix, okay? So, and all these operations are described by these graphs. Then you can do fancy stuff. You can have hidden layers that are composition of other hidden layers, which is like you can have hidden layers that are like sums of two previous hidden layers, for example, right? Which is this, okay? So this graph is exactly the way the engine, the Torch engine, sees your neural networks, right? And it uses this to do automatic differentiation, okay? So then you can apply nonlinearities to whatever comes out of your hidden layers, like hyperbolic tangents or sigmoids, or all sorts of sigmoids or ReLUs or whatever. And it's very easy because you have, for each of the tensors, you have all the nonlinearities already implemented. You just call the type of nonlinearity that you prefer, and then it applies it to it. And the simple thing is that once you have defined all the network, if you want to backpropagate gradients, you just call at at the node of the graph where you want to start your back propagation, which Andreas told you about, you don't need to calculate the gradients. You just need to have the gradient with respect to that node and then call dot backward at that node. Okay? So here, if you want to call dot backward at next h, which is the output of the network, you just call it and it will backpropagate a tensor with filled with ones of the dimensionality of the output. Okay. Has anybody managed to get the Jupyter? No. Do you guys have you connected? Hmm? Okay. So, are they on Windows or no? Okay, so what I will do is I will send you the online links to the notebooks that you should have been using now, but for some technical reasons it seems that it's not possible. But then, you know, they're very pretty straightforward, and everything is explained in the notebooks. I encourage you very much to try them and walk yourself through the examples. And you know, what we'll do, we'll set up a group, and then if you have any question, just feel free to ping me, and then I will answer those questions. Okay? But it's, yeah. What's the what? The difference between PyTorch and TensorFlow. The difference between PyTorch and TensorFlow is PyTorch is good and TensorFlow is not good. No. No. Actually, there is a fundamental difference. Let's be more serious. In PyTorch, you have both of them allow you to build complex model in a very abstract way by using minimal instructions. But PyTorch uses something called a dynamic computation graph. So in TensorFlow, what you do is you define your computation graph. So, and then you compile it, and then you train your model. In PyTorch, you can define your computation graph and then add nodes in the graph while you're training your models. Because the computation graph is dynamic. You can have if, you can add if expressions and all of these things that you cannot do with TensorFlow. It's way more flexible. There are other frameworks. I don't know does MXNet have a dynamic computation graph? Does it have? The dynamic one? No?
You mean where you can change it?
Yes.
I'm not sure if it's in or not, but it was on the flip list. Yeah, is it in now?
Yeah, it's probably available with MXNet as well, but it's definitely not available with TensorFlow. So there are some models that that I have shown here that you cannot do with TensorFlow, or it will take you more time to do it with TensorFlow. It's way more flexible. Yeah. And also the integration with Numpy is it's more tightly integrated with Numpy. So if you know Numpy, it's very easy to understand any code that is written in PyTorch. It's a bit more complicated if you want to do it with TensorFlow. And also, PyTorch is faster than TensorFlow. Oh, no, TensorFlow. TensorFlow. Yeah. Yeah. So yeah, you can define neural networks. So the neural network that Andreas presented you can define it very easily with this number of lines as a class, right? In fact, this one is more complicated because it has more layers, and it's as easy as this. You add layers by adding, by just calling some building blocks. Fully connected is NN. NN is the neural network package of Torch. If you call NN.linear, it creates a linear layer for you. You could add all sorts of layers. I mean, all the layers are already implemented. You just call them, specify the dimensionality of the matrices that are to be built, and then that's it. You're good to go. Okay. You have all the optimization algorithms that are frequently used to train neural networks already implemented in it. You have SGD, Autograd, RMS prop, LBFGS, all of these things. Usually you don't need them. SGD very much does the job, except in some cases. But they are here if you want to try them. And also, one thing that is important is that more and more people are using this. And the benefit of that is it's very rare that you will have to implement your model from scratch. Whatever model that you want to do, someone has probably already done it and pushed it somewhere. You can find it on GitHub, edit the code, customize it to your needs, and then run your problem, solve your problem more quickly. Okay. Is it working? Okay, so let me just show an example here how I can build a very yeah. Okay, so yeah, this is the traditional workflow. You just call the torch, right? And then if you want, you can have this. You can declare a linear layer, for example. Okay, so you can declare if you assume that our input is of dimensionality 10 and the hidden layer is of dimensionality 20, so you can just code this. So this gives you your first a linear layer. So if X is your input, whoops, no internet. Oh, it's back. Okay. Oh, it's working? Okay. If it is working, I can actually directly connect to this thing. Maybe. Yeah. Oh, is it? No? Okay. Submit query. Sorry. Oh.
Sorry, yeah, that's everyone else's learned that, so.
Okay, so.
It's my fault. I changed it to that to demonstrate.
Okay, so now, okay, I see.
Oh, you're not on here,
Yeah, but I do have internet actually, but I just don't know where they are in the. So, do you guys can see the notebooks now? Who can see the notebooks? Just one person?
So definitely, I can see that. I can see.
So can we just? And you can go. This is the PyTorch website, so you should go here. You can download the software here, install it on your own machine, local machine, but you have example projects here. Okay, so these projects. These projects, you have the GitHub for this project. It gives you probably the base code that will allow you to do whatever you like. I mean, all the examples that I have shown, you find the code to reproduce that here. You have state-of-the-art models, for visual recognition that are already trained here with an ImageNet. You can train, you can do distributed training. You have reinforcement learning examples. You have sequence-to-sequence prediction models like translation models and all these things, language modeling. You know, you have all sorts of examples here. So I encourage you to go and check these things up. But that's for the example projects, which may be more complicated at the beginning. But what you need to do first is to go to check up the tutorials, right? We have put together tutorials, and you know, we have put together tutorials, and these tutorials cover almost anything that you may need to start. And this 60-minute blitz of PyTorch is basically the notebooks that I wanted to go over. Okay? So if you have the notebooks here, right? So what it does is very simple. It's what I have explained already. I think I will just go to the next one. Yeah, so the basic thing is to know that if you declare the network, you have to declare the inputs to the network as variables. Okay, so this is the basic way of doing it. And then after you have that, everything else is very simple because the gradients are automatically calculated. Just call out.backward if out is the output of your network. You can print gradients. You can have complicated formula and let the engine calculate the gradients for you. And all of this is just one instruction in general. Like whatever formula you write, just .grad gives you the gradient. You know. So the most complicated, this is the architecture that Andreas did show you. If you go over the notebook, it's defined here, this architecture, right? And it's well commented. So it's just building blocks, linear layers, convolutional layers, everything is already implemented. So you just need, if you read a paper and they say this is how we do it, this is the architecture, you can build the exact same architecture by using this because all the building blocks are already here. Okay. So the cool thing is the most complicated architectures that you have seen, whether it is Inception or ResNet or whatever, they're already coded and you can find them in the example projects in the GitHub. So you can go there and download the same neural network that Google is using in production or Facebook is using in production and start using it for your own application. And it's already trained and everything is there, right? Yeah, so that's basically it. It's unfortunate that we could not go over the IPython notebooks, but if you have any question, just drop me an email or let's just keep in touch on Facebook. If you have any question. Yeah, I will be around. I'm around until Saturdays. So if you want to go over these IPython notebooks, if you have any question, just yeah. No, you can use it without CUDA. Is just if you want to train this network with GPUs. So one thing you need to know is if your project is big and then you're training all this complicated architecture, it's better to have a GPU on your computer. But if you're solving simple problems, you don't need it. But in some problems, it's literally impossible to train them on standalone machines without GPUs, unfortunately. And that's one of the limitations of these models. That's one of the limitations of this model. Any question? Okay. So thank you.